Point three, I'm going to discuss some of the important properties of objects experiencing projectile motion. What is a projectile? A projectile is an object that's in free fall with some sideways motion. And objects that are in free fall have no drag force acting on them. The only force acting on an object that's in free fall is gravity. And if we draw a little diagram to show what's going on with the forces acting on an object that's experiencing projectile motion, we'll draw something like this. The force is acting downwards on our object. An unbalanced force will cause an acceleration in that direction. So the direction of the acceleration is down. Gravity does not care what the object is doing. Gravity is always pulling down, and it is always causing an acceleration that is down. Doesn't matter if the object's moving up or down or sideways. An object is accelerating down. So that acceleration is down, which means that it is not side to side. There is no horizontal acceleration. And so we then have the components of the acceleration for an object in projectile motion. We can say that the object's horizontal or x acceleration is 0, and we can say that the y acceleration or vertical acceleration is g downwards. And typically we will choose up to be our positive y direction. So typically we will say ay is negative g. And g, you should remember, has a value of right about 10 meters per second squared. That's the value that we're going to use for tests and for positive physics. But if we're testing the value for g in the real world, g in the real world has a value of approximately 9.8. The second idea that we need to keep in mind is that the x direction motion and the y direction motion are independent of each other. By that I mean that the x direction motion does not affect the y direction motion. They are independent of each other. So what does the motion in each direction look like? Well, we know that the motion in the x direction has to be constant velocity. Why do we know that? Well, we know that because the acceleration in the x is 0. The acceleration is only in the y direction, is not in the x direction. And with 0 acceleration, that means that the final x velocity has to equal the initial x velocity. So the velocity in the x direction does not change. It maintains that same x velocity all the time. And so if we have our projectile, and we imagine that we throw the projectile sideways, well, the sideways motion is just going to look like this. It'll move that distance in 1 second, the same distance in the next second, the same in the second after that, the same in the fourth second. The motion in the x direction is constant velocity. What about the motion in the y direction? Well, in the y direction, we have uniformly accelerated motion. We have an object that's moving with acceleration, and that acceleration is always downward. So, in my example here, where we have an object that's moving with that's thrown sideways, in the first second, it's going to move downwards just a little bit, and in the next second, it'll move a little bit further. In the next second, it'll move a little bit further, and then a little bit further after that. So if I add my x direction motion represented by the red arrows to my y direction motion represented by the green arrows, well, if I add those green arrows in at the tip of all the red arrows, you can see that we have a familiar path. We have this parabola, and the trajectory of an object, that's the path that the projectile takes, is always going to be a parabola for projectile motion.
Because there is only an acceleration in the y direction, but the motion in the y direction is completely independent of the x direction. The x direction doesn't even know what's going on in the y direction. In the x direction, if I throw an object like this, the x direction simply, very boringly, moves with a constant velocity. There is no time dependence. And the y direction on its own does its own thing. It goes up, comes to a halt, and it stops. And of course, the actual motion is the sum, the superposition of the two. We have tried to find a way to demonstrate this quite bizarre behavior, which is not so intuitive, that the x direction really lives a life of its own. The golf ball goes up and comes back here. Not here, not here, not there. That's easy. You can shoot it up a little at an angle, and the golf ball will come back here. Once we have achieved that the golf ball will come back there, then I'm going to give this car a push. And the moment that it passes through this switch, the golf ball will fire. So the golf ball will go straight up, as seen from the car. But it has a horizontal velocity, which is exactly the same horizontal velocity as the car. Let me first show you, otherwise if that doesn't work, of course it's all over, that if we shoot the ball straight up, that it comes back here. If it doesn't do that, I don't even have to try this more complicated experiment. So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps perhaps it would help if we give it a little bit of leeway. The gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works.
Okay, the video that you just watched really tries to drive home the fact that we have independent x and y motion for objects in free fall, in projectile motion. We have constant velocity in the x, and we have acceleration in the y with an acceleration of g downwards. So let's see that in an example on the next slide. Here we have a rescue airplane that's going to drop a package while moving with a constant horizontal speed. If we assume that drag is negligible, and that's a phrase that should tell you that the package is going to be in projectile motion, in free fall motion. It wants to know where will the package land relative to the plane. So the first thing that we have to realize is that the motion of the airplane is constant horizontal motion. And so what's the package going to do? Well, the package, if you drop a line directly beneath it, the package is going to move horizontally that same distance. And so where's the package going to be? It's going to be at point B, directly beneath the airplane. This is kind of just the reverse of the video that we just watched, where the video shows a cart that stays beneath the ball while the ball is in projectile motion. Here, the package will maintain a position directly beneath the airplane because they share that same constant horizontal speed. Okay, one more example. Here, rock A is dropped from the top of a cliff at the same instant that rock B is thrown horizontally away from the cliff. The rocks are identical. We want to compare their graphs. So it's really important that this phrase here, that the rock B is thrown horizontally and rock A is dropped. That is going to tell us what's going on with the rock's velocity initially. So for rock A has an initial velocity in the x direction, 0, because it's dropped. Same thing for our y direction velocity. Okay, for rock B is thrown horizontally. So rock B will have some initial x velocity that is not 0. And we're going to assume that the right is our positive x direction. For the y direction motion, starts with zero velocity. That's because a horizontally thrown rock has has zero y velocity. All of its velocity is in the x direction. None of it is in the y direction. So what do these graphs look like? So for our dropped object, there's no motion in the x at all. The initial velocity in the x is zero. The acceleration in the x is zero. So we will have constant zero velocity in the x direction. So what about the y direction? So it's important to keep in mind that that the acceleration is the slope of this graph. There's a slope of negative g because there's an acceleration of negative g in the vertical direction. And our graph should start out from the origin because the rock A is starting with zero y velocity. So we should get a graph that looks like this, where the slope is equal to negative g. Over to rock B. Rock B maintains a constant velocity in the x direction. We know that because there is no acceleration in the x. So we should be graphing a horizontal line, but we should be graphing a horizontal line that is above the x-axis. That's because the initial x velocity is non-zero. It's some positive number. Now, what about the y velocity, the y motion? Here we should get the same graph as for rock A, and that's because they have the same y motion. They have the same acceleration in the y, they have the same initial y velocity, and so we should have a straight line with a slope of negative g that starts from the origin. Okay, in this example, we're analyzing the same situation where rock A is dropped from the top of the cliff and rock B is thrown horizontally away from the cliff. Here we want to compare the times. And this is going to lead to a really surprising result. Okay, so first we're going to analyze the motion of rock A. Rock A is only moving in the y direction, so we only need to really analyze y direction motion. And what do we know about rock A? Well, we know that rock A is starting from rest. We know rock A is going to move downwards in the y direction. So here I'm using delta y instead of delta x because delta x is zero. We only care about y direction motion here. So I'm going to use y's instead of x's. Here, the change in the y position is going to be negative because the rock A is going to fall downwards. And that change in y position is going to equal the height of the cliff. So the rock A is going to have a change of position of negative the height of the cliff. The rock is going to be in free fall, so it will experience a acceleration equal to g, also downward. So I'm going to give that a negative sign. And we want to know what is the time for rock A to hit the water. So I need an equation that relates these four variables. And this equation is on your equation sheet, except it has delta x, where I wrote delta y. I'm just switching the notation a little bit to note that we're looking at y motion instead of x motion. And if I fill in all of my variables that I have here, I can solve for t. Okay. I have a negative sign on each side of the equation. I can now get rid of my negatives. And I get h is equal to 1/2 gt squared. If I multiply both sides by 2, that gets rid of the 1/2. I can divide each side by g. That gets me t squared. And the last step in the algebra would just be to take the square root of both sides. So rock A will reach the ground in a time that's equal to 2 times the height divided by g under the square root. I have an expression for the time that it takes rock A to strike the water. So now we're going to move on to rock B. Now, rock B has some sideways motion, but the sideways motion does not affect the time of flight. It's only the y direction motion that's going to affect rock B. So, what about rock B's y direction motion? Well, rock B, as I discussed on the last slide, starts with 0 y velocity. The velocity of rock B just looks like this initially. It does not have any y component. All of its initial velocity is in the x direction. Rock B is going to have a change in height that is also negative h, negative because it's downward, h for the height of the cliff. It will experience a y acceleration also equal to negative g. And we want to know what time rock B will hit the water. If you see where I'm going with this, well, the same equation relates the variables. Now, where did this equation come from? Because this you won't find on the equation sheet. Well, on the equation sheet, it looks like this. And you notice I just swap out x for y and all the other things. So delta x is a vector, v initial is a vector, a is a vector. All the vector quantities can get separated into components when we have to consider a two-dimensional type of problem. And this is a two-dimensional problem. So where I have initial velocity, which is a vector, I put in a y component subscript. Same thing for the acceleration. The acceleration in the y direction would get a y subscript. And so if I put in my variables, you'll notice that this line is the same as the second line from rock A. So guess what? The time that it takes rock B to reach the ground is exactly the same as the time that it takes rock A to hit the water. And why is that? Well, the x direction motion, that's the only difference between rock A and rock B. Rock A and rock B have different x direction motion, but that does not affect the y direction motion. Rock A and rock B have identical y direction motion. And you're going to see that in the video that I'm going to put in after this slide, where we're going to see a dropped object and a horizontally launched object, and they will hit the ground at the same time.